This video is on atomic radius, trends in atomic radius in both columns and periods or rows, as well as how radii change when atoms lose or gain electrons to form ions. Now there's three variables that you look at, and you should look at them in order, in descending order of importance. In other words, if two things have different numbers of principal energy levels, that's the only thing you really need to look at. That should give you a good idea of which one has a larger radius versus a smaller. If the two things you're comparing have the same number of energy levels, you switch to looking at nuclear charge. And if those two things are exactly the same, then the only thing left is to look at the number of electrons. Please let me make it perfectly clear. The number of electrons is the last thing that you look at. You first compare energy levels. Secondly, you compare nuclear charge. So if you're looking at, let's say, a column, right? And let's say we're looking at the alkali metals. So we have a family, right? And we can pick any family in the table, but this one here is the alkali metals, right? Those active metals, right, that are very explosive, okay, and very unstable. Each of these guys has one distinct difference. When you go down the column, see, lithium is in row 2, sodium is in row 3, and potassium is in row 4. And because that, we know that lithium has 2 energy levels, sodium has 3, and potassium has 4. The assumption is you can think of these as being layers. So if this is your nucleus, lithium has 2 layers of electrons, or shells. And by the time we get to potassium, we have 4 layers, or energy levels, or shells. And it's a really obvious relationship. This is a direct relationship. So whenever you go down a column, the radius is going to increase. And if anybody ever asks you why that is, you can say that the element that's further down in the column has more principal energy levels. So radius increases, okay, because we have more PELs. And you want to note that this is a direct relationship. So the relationship between principal energy levels, okay, and the size of the atom or its radius is a direct relationship. So more energy levels, bigger atom. All right, that's the trend for any column, right? So you can assume that, let's say, since fluorine is here and then chlorine is right below it, you can assume chlorine is larger, it has more energy levels, and you can pick any other column. Now a row is a little bit different. For those who graph the trend, what you're going to notice is if you start off at the beginning of a row, let's say you start with sodium, as you go down to argon, the radii tends to get lower and lower as you go across in the row. Now this might be counterintuitive because as you go across in the row, you're adding more protons and more electrons. Sodium has 11 protons and 11 electrons. Argon has 18 protons and 18 electrons. But what you want to recognize here is if you go through the criteria, the first criteria doesn't count. It's not the number of electrons. That's really important here. All right? As you go across in a row, the number of PELs stays the same. So PELs, number of energy levels, basically remains the same. So we can't look at that criteria when we're comparing these atoms. So then we go to criteria number 2, which is the nuclear charge. Now, you have to picture what's going on in the atom, or think about forces. Protons have the opposite charge of an electron. And the protons that are inside this nucleus, okay, they're pulling those electrons. So here's your nucleus, right? It's literally pulling the electrons towards it. Now, as you go across in the row, the nuclear charge changes. The nuclear charge is just the atomic number. So the nuclear charge for sodium is plus 11. And the nuclear charge for argon is plus 18. Now this is an indirect relationship. Whenever you go across in a row, the radius will always get smaller. And the reason why it will get smaller is because while the principal energy levels remains the same, the nuclear charge increases. And this draws the electrons in those energy levels closer to the nucleus. All right? And so as nuclear charge increases, the radius is going to get smaller, assuming the number of energy levels is exactly the same, which it is for a row. So it doesn't matter what row you're talking about. As you go across the row, the smallest radii, okay, are going to be over here on the right, and the largest are going to be over here on the left. So just to reiterate really quickly, as you go down in a column, radius gets larger because of more energy levels. As you go across in a row, the radius gets smaller because you're adding more protons to that nucleus while the number of energy levels remains the same. Notice I haven't even mentioned number 3 yet, have I? That's only going to come up in one particular place. So let's talk about ions. Now, metals and nonmetals do different things when they form ions. Metals tend to lose electrons. So sodium, which is 2-8-1 as an atom, will lose its one valence electron. Okay, and that will go somewhere else. It will give it to some nonmetal, maybe fluorine. Okay, and when that happens, the sodium ends up being 2-8. Now, I put our 3 criteria over here to the left, okay, so we can go back to them. And again, we're going to start with criteria number 1 and see if that explains what happens here. Well, if you look at a metal and the metal ion, which is a cation, remember that's the positive ion, right? What you can see here is that essentially when the metal forms an ion, it loses an energy level. Now, some of the transition metals will lose a sublevel, but you can just view it whenever a metal forms this cation, it's going to lose an energy level. And if it loses a layer, it's going to get smaller. So automatically, metal ions or cations will always be smaller than a metal atom of the same element. And that's because it's got less PELs, or principal energy levels. Now, if I look at nonmetals, we have a different situation because nonmetals tend to gain an electron. When they do this, they tend to complete their shell. So F now has a complete octet. By the way, when we draw negative ions or anions, we tend to draw brackets around them with a charge. So this is an anion. Now, what I want to do is go through the 3 criteria, okay? I'm going to tell you in advance that for nonmetals, they tend to be the opposite of metals. So the anion is going to be larger than the atom. So a fluoride ion is larger than a fluorine atom. And you can say that for any anion. The reasoning, though, okay, we have to go through the criteria. So we look at it. Do the number of principal energy levels change? And the answer to that is no. They both have 2 energy levels. Does the nuclear charge, which is just the atomic number, change? No, both fluorine and the fluoride have 9 protons in their nucleus. So the number of positive 1 charges in there, total plus 9, is the same for both of them. So now, and this is the only time we're going to look at criteria number 3, the number of electrons. Now, this is a direct relationship. If you add a few more electrons, they tend to repel each other. And when things repel, they tend to spread out. And that's what makes it larger, because the repelling electrons spread out. So, to review, metals always lose electrons, and they always lose an energy level or a sublevel, and in doing so, they will always be smaller than the atom. So cations will always be smaller than the corresponding atom. For nonmetals, it's the opposite. And the reasoning is completely different. So for nonmetals, they're gaining electrons, and those electrons repel each other, and the ion is a little bit larger than the atom. Last thing, isoelectronic species. Iso means same. Electronic means electrons. So these guys all have the same number of electrons. So what I've written down is their shell configuration, or the shorthand, okay, from the periodic table. What you want to recognize is they all want to be like the noble gas that's between them, right? So oxygen is atomic number 8. It wants to be like atomic number 10, neon. Fluorine wants to become fluoride. And the way it does is by gaining 1 electron. So our oxygen gains 2 electrons and becomes 2-8. Our fluorine becomes fluoride and gains 1 electron, becomes 2-8. Our neon was always 2-8. Sodium, which was 2-8-1, loses an electron to become 2-8. Magnesium loses 2 to become 2-8. And aluminum loses its 3 valence electrons to become 2-8. And they all become iso, or same, number of electrons. Nice, easy idea. And they all get that stable octet. So, which criteria do we go to? Well, we obviously can't go to PELs because they all have exactly 2 principal energy levels now, don't we? They all have a different number of protons in their nucleus, though. They all have a different atomic number. They all have a different nuclear charge. Now, make sure we're clear. We have to get comfortable with indirect relationships. The relationship between nuclear charge and the size of the atom is an indirect relationship because And the reasoning is because if the nuclear charge is stronger, it pulls the electrons in closer to the nucleus, making the thing smaller. Therefore, aluminum, which has a nuclear charge of plus 13 versus oxygen with a nuclear charge of plus 8, this has the biggest nuclear charge. All other things being equal, it's going to pull on those electrons to a greater extent. It's got what they call a greater effective nuclear charge. Therefore, this will be the smallest. This will be the largest. And the pattern is a straightforward pattern. From the smallest nuclear charge being the largest of the isoelectric electronic species to the one with the highest nuclear charge having the smaller radius because it pulled the electrons in the most.